All right, yeah. Hi, everybody. Here we have a talk with Tim Holme of Quantumscape. So Quantumscape is developing new battery technology to make electric vehicles cheaper and faster to charge and longer range. And they've been using AI at several different stages of their manufacturing process, from material discovery to quality control. They also happen to be one of the so far relatively rare but existent climate tech unicorns. So I think that's really exciting. And Tim is the co-founder and CTO of this company. He has an extensive background in physics, material science, and electrochemistry, and he founded Quantumscape in 2010. Tim has also taught Bayesian machine learning at Carnegie Mellon University. And yeah, with that, on to Tim. Please go ahead, Tim.
Great. Thank you very much for the introduction. It's good to be here with you all. Let's start with a brief agenda of what I plan to cover today. I'll just give a brief introduction to Quantumscape so that you have a sense for the context in which we're operating and solving some of these machine learning challenges. And then I've got about 4 case studies that I selected to show you sort of the range of how we apply machine learning or AI on our data. So to jump into a background of the company, we've been around for about 10 years. We were founded in 2010. We've spent over $300 million on our development to date. So this is the problem of inventing a better battery is not one like making an app, which could conceivably be done with a few people, and then scale it up to the iTunes store. It's something that really requires massive equipment, therefore massive investment. So our team at this point is over 300 employees, and we've got over 200 patents and patent applications as well as a lot of trade secrets. So there's been a lot of invention to date and a lot of scaling still to go. I think we're all aware that automotive vehicles contribute a lot to climate emissions and greenhouse gas emissions. This schematic is one way to represent the electrification trend. So there are about 100 million cars sold per year in the world today, 100 million vehicles. And this fraction here that's green in the upper right is about 3% of that market that is currently substantially electrified, either plug-in hybrids or full battery electric vehicles. It's our mission as a company to make not an incrementally better battery that could address this 3% of the market, but to make a step change in battery performance that could enable batteries to break into this massive mass market. And we think that to do that, the battery needs to improve on at least 5 key metrics. Need to increase the range of the vehicle, decrease charging time, lower cost, extend the lifetime of the vehicle, of the battery, so that it lasts at least as long as the vehicle does, and finally improve on safety. And if you do those 5 things, you can meaningfully close the gap between today's battery electric vehicles and combustion engine vehicles and get to that tipping point of mass market adoption of EVs. And so this is one schematic that shows our approach to be able to solve all of those 5 challenges at once. It's very hard in batteries to make simultaneous improvements. It's much more common to make an improvement along one dimension and then sacrifice performance along another. So without going too deeply here, on the left, I've got a schematic of a lithium-ion battery with the key functional layers here, including this graphite anode and an oxide cathode material and the separator in between. What we're doing is essentially eliminating this graphite anode material and moving over to a battery architecture that has no anode in the as manufactured state. And to do that requires replacing this porous polymer separator with a solid state separator here. And then when you charge up the battery, the lithium from the cathode plates as a metallic form on the anode side. And then that is the lithium that goes back and forth as the battery charges and discharges. So it's a pretty large design change to a battery that requires new materials. We didn't invent this idea of using lithium metal as the anode material, but we do think that we're innovating along the dimensions of making this battery practically useful, safe, and scalable at low cost. And so what we have shown so far is that this is right here is a very thin ceramic flexible material. This is the key functional component of our cell that was shown here in this schematic. And then based on that separator, we've made single layer and then multi-layer cells, prototype cells still. And we are now getting into pilot stage and ramping up into commercialization of this technology. And so now to transition a little bit to how we use data and machine learning at Quantumscape. So I'll talk today in the 4 case studies about quality control of the manufacturing process. So we take a lot of images. We've developed custom imaging systems to image all of the components of our battery and therefore do quality checks with them. We're generating about 700 gigabytes a day of those images. We take a lot of electrical test data of the batteries that we produce, and so we're producing about 2 gigabytes a day of pretty compressed electrical test data that describes how the batteries perform as you charge and discharge them. Then we also have time series data around our lab and factory. Every instrument that produces a data stream, we consume that, and so that's about 1.5 gigabytes a day. So it's not on the scale of Google or Facebook by any means, but it is still a substantial amount of data. So we have adopted a lot of the best practices today, Kubernetes, Docker, Jupyter Notebooks, et cetera, to enable both our data scientists as well as the material scientists, the chemists, et cetera, to get access to their data and make powerful inference with that data. So now to get into some of those use cases here, I'll go through 2 case studies on battery electrical data. The first one will be on a parametric curve fitting. So I don't want to get too deep into the electrochemistry of this problem, but I do want to describe the problem enough so that you understand why it's interesting, why it wasn't trivial to solve, and how our solution is nice. So this technique that I'll be describing is a technique that pinpoints where the largest resistance in the battery originates, what material or what interface is high resistance. And you often need to know that as a battery designer or developer, because you want to reduce the resistance, the internal resistance of the battery, so that it can deliver higher power, that is, recharge faster. So if you're trying to develop a battery that can charge very quickly, you need to be able to do this diagnostic test on a battery and then analyze it and break down that data to let it tell you where the largest resistance is, therefore where you should be focusing most of your effort. So this impedance that gets measured is a complex function of frequency. So you'll send in a time-varying signal like a sine wave, and then you measure a time-varying response, and then you work with it in the frequency space, in the complex frequency space. Now there are a few Python packages I point out to here that use least squares fitting to be able to fit this data, and they rely under the hood on SciPy packages and lmfit. However, what I'll show you is that out of the box, they're usually not good enough, or at least what we found in our cases is that they're not good enough. So the problem statement here is that the fitting using these packages is often of poor quality, even after you do a manual tuning to initialize parameters to these optimization functions. So I'll just give you an example. This was one, I literally just pulled this at random out of our database. This data, the blue points are measured data. I just pulled the first one that came up when sorting by random order. And then I did a little bit of manual tuning and then used these packages to produce the orange fit. And what you can tell is that this orange fit is not a good fit to the blue data points, even without understanding all of the complexities of what this data represents. It's an inadequate fit, and that's the problem statement. So what did we do about it? Well, we attempted a lot of different homegrown fitting solutions using genetic algorithms, the Metropolis algorithm, PySwarm, which is a particle swarm optimizer, and as well as neural nets. And after a lot of different playing around and manual tuning, the result that we now have deployed in production is one where 98% of the fits are acceptable with 0 manual intervention. It's a fully automated pipeline. So it's not 100% there, but it's good enough that that our researchers can use it to draw sound conclusions on and move forward with. What I'm showing here is a cumulative distribution function of the root mean square error of the fit relative to the data. And we set our quality threshold of about a 10% error rate. And so you can see that well over 90% and 98% of the fits have very low errors. And then there's this high tail of 2% of the fits that have high errors. And there, because we produce a diagnostic, a goodness of fit, the researchers can just discard these 2% of poorly fitting data points. And so just to come back to this data that I showed you in the last slide, the red curve is the curve that was produced by our fitting algorithm to these blue data points. So you can see, and I literally just picked one at random, so no cherry picking of data here, but what you can see is good fit. So this would be the case in 98% of the time. This has a root mean square error of 0.29%. So this is one use case, parametric curve fitting, which is out-of-the-box solutions are not very good, so we developed our own. Some of the takeaways from this project were that we had to do some data normalization. So in this case, the data is distributed over logarithmic space. So when we took the logarithm of all the data, that was normalized into data that the optimizer could work better with. We also used constraint optimization by applying some of the right constraints and really drawing on the domain knowledge of scientists who work with this data. We were able to come up with good constraints that could enter into a constraint optimizer and then get much better fits. So these were some of the takeaways of working with the domain experts. Next problem in electrical test data here was classifying the electrical signals. So here we are cycling a battery, charging and discharging it. And these charge-discharge measurements carry signals embedded in them of the battery performance and the battery state of health. So just like your iPhone doesn't last as long today as it did when you bought it, every battery degrades over time and over usage. And so what we were trying to do is pull out some of this information from the battery cycling curves so that we could come up with good diagnostics to use in accelerated life tests of the batteries. So basically, when you're cycling a battery, you apply a time-varying current and you measure a time-varying voltage. So this is a voltage as a function of time that gets measured. And then we're trying to extract information from that. So the problem statement in this project was to try and determine the battery state of health from this measured voltage as a function of temperature of time. One reason this gets complicated is that the tester itself can have anomalies. There can be poor intermittent electrical connections. That doesn't happen in the majority of cases, but even in corner cases, you want to make an algorithm that's pretty robust to the 1 or 2% corner cases. There can be temperature fluctuations in the ovens and fridges where we put the batteries for their cycling tests. There can be power outages. This happens. There can be other reasons that there are test anomalies. And part of the complication of this problem here was to create an algorithm that was pretty robust to all of these anomalies. So I'll give you a little bit of example data here again. So in the top right, I'm showing you some voltage information that was measured as a function of time. So you've got time on the x-axis, voltage on the y-axis. And then what we were trying to do is classify this into several different characteristic types. And I actually colored these curves by, you could say the manual data labeling process, or basically what we wanted to achieve. And you can see that looking at the data this way, it was pretty unclear to even a human, let alone an algorithm, how you could come up with these different classes for curves that look pretty different. So the first step we did is to scale the time and voltage so that they went between 0 and 1. So this is just data normalization. And then here you can start to see a little bit more of the regularity. So the bottom right curve is the exact same data as the top right, only it's been scaled so that everything falls between 0 and 1. And then you can see, okay, these orange ones are ones with a large drop, and then they become flat. The blue one, for example, is the highest, and there are several different shapes in between that we wanted to capture. So to address this problem, we built a data labeling pipeline. We labeled about 10,000 signals by hand, and also in the process built a crowdsourced labeling tool into the researchers' workflows. So we have some internal software that they use to visualize their data. We built some labeling tools into that so that we could extract more labels from everybody who's looking at their data. And then we built a classification model on top of those labels. We tried various things like decision trees, XGBoost, random forest, you name it. We tried it, basically, even some recurrent neural nets. For hyperparameter tuning, we tried things like hyperopt and Bayesian optimization as implemented in Dragonfly, also random search. And then we also had to do several iterations of active learning on top of that. And the result here was that area under the curve of the receiver operating characteristic of about 0.997 on a difficult test data set. So we selected a test data set of some of the most difficult examples to classify, and then measured performance on that holdout test data set and found that it was rather good. And we deployed this as an API in production using Waitress and Flask. And then we do retuning as required if the data drifts. So this labeling tool is still a part of the researcher's workflow. We still harvest labels. We don't have an automatic tuning and deployment because basically we didn't trust the algorithm to be trained on itself without a human in the loop because we didn't want the model performance to degrade. So it's still a human in the loop retraining process, but we do that. And then this is one graphic that we use to evaluate performance here. This is just a precision recall curve, precision on the y-axis, recall on the x-axis, and several of the metrics that we look at. How many samples in the test set, the area under the curve, the F1 score, and then we also created these other metrics of the maximum recall at high precision and the maximum precision at high recall. And we evaluate models according to all of these different metrics to select which model to use and which operating point to use on the model. Some of the takeaways from this project are class weighting was very important. This new tool of histogram gradient boosting, at least new to the scikit-learn package, turned out to offer good performance. And then also crowdsourcing labeling made it a more scalable project. And here by crowdsourcing, I don't mean Mechanical Turk. This is all still internal to employees at the company, but just basically democratizing a little bit this data labeling process. So I'm going to speed up a little bit here. I know I've been going fast, but just to fit within the allotted time. We'll now talk quickly about some machine learning we've done on component image data and go through a couple of case studies. So we take the components of our battery and then subject them to different imaging types and then want to be able to characterize that image in terms of a number. So if you are, say, a process engineer who's in charge of running a process, your objective is either to maximize the output of your process or minimize a bad outcome of the process or control your process within certain specification limits. And you can't do any of that with an image. You need a number to be able to do that and run statistical tests on it. So our task here is to turn images into numbers that process engineers can use. So this first case study here is on electron microscopy. So an electron microscope, similar to a light microscope, but uses electrons because electrons have a shorter wavelength than light, so it can image with higher resolution. We have over 5 electron microscopes in the company that are in operation literally 24/7 because these are the tools that are most in demand by the researchers. It's really like a picture tells it's worth 1,000 words kind of a situation. Everybody wants to see what they've made at extremely high resolution to assess their quality. So the problem statement here was to quantify the size distribution of some of the structures that we observe in a microscope image. And I'm not able to share with you any of our actual images here. So I picked an image of an analogous program in biology here, one of cell segmentation. So if you're a biologist looking at cells in microscopes, you often need to be able to outline or segment the image to say, this is a certain cell and this is a different cell. So it's a similar task that we have. So we bootstrap the data by using conventional image processing to generate labels, things like a watershed algorithm, histogram equalization to be able to generate our first labels. And then we trained a neural net using the Google AI platform. Some of the challenges we had along the way is we found that in the Google AI platform, at least today, it accepts a max image size of 256 pixels. And they didn't use floats, just ints here, because the request size through their APIs would be too many bytes if you used a float at every array value. And our images are high resolution enough that we found that using a float, at least in our internal algorithms, would be better than using ints. So these are some of the challenges we had. Along the way, we did some developments here. And I think we have superior performance from this Google AI neural net relative to the conventional image processing that we use to generate the labels. And then we have deployed this with a Google Vision API. And just to show you some of these results here, one way we assess success is by looking at the R-squared and the goodness of fit between values extracted using the deep learning image processing and conventional image processing. And what we found here is a good R-squared of about 0.96, close to a linear fit. And when we go through and inspect both our image processing team as well as the domain experts, when we go through and inspect the outliers that have the worst fits, the consensus among this panel was that the deep learning was doing a better job than the conventional image processing. So usually these outliers here are outliers because the deep learning algorithm has done a better job. So some of the takeaways are we had to do a lot of data cleaning in this process. and also that this Google AutoML isn't yet flexible enough, at least for some use cases, although it is a great tool that can put AI into the hands of people who aren't deep learning experts. Final case study here was on defect detection. We have custom imaging systems that look for defects in the parts we produce. We use that for quality control and process feedback. And we've deployed a lot of different imaging stations here that produce different image types. So our problem statement for this project was try and quantify the size, position, and frequency of 12 different anomalies that showed up in the images. And again, I can't show you images of our components for proprietary data reasons, but I pulled some analogous problem from online. This was defect detection of other manufacturing flaws. So you could see like a line here and a different kind of a scratch mark over here. So these aren't the defects that we're looking at, but it's analogous. So here we had, again, manually labeling to start the process. Then we trained an efficient det on Kubeflow and tensor processing units on GCP. We used pre-trained weights, and then we also downsampled the image a bit to make it run more efficiently, make it train faster. Our result here was that our precision and recall varies by defect type, but we were getting reasonable F1 scores of between 0.94 and between 0.99 on some of the best classes, the largest classes and the best classes. Here breaks down some of the performance on some of the classes. But some of the takeaways here is that building the infrastructure up for model lifecycle management is worthwhile once you have at least, call it, 3 machine learning engineers. You know, every machine learning or AI engineer probably needs 6 or 10 data engineers behind them to do DevOps and data pipelining and data capture and everything else. But once you have scaled up the team enough that you've got several people doing machine learning simultaneously, then it really pays to build some infrastructure. So we haven't done as much as larger companies out there have, but we are going through that learning curve. So just to summarize, Quantumscape is aggressively adopting new data pipelines and data processing techniques. However, there's still a lot more to do. There's a lot of, I would say, low to medium hanging fruit around for very talented machine learning or data science engineers here. So we are seeking talented folks to join our team. In data science, data engineering, image processing, and more. We've got a lot of job posts on our website. So if you are interested, you can visit our website, quantumscape.com, and find the careers link there. And I will stop here for questions. Sorry, Eugene, I can't hear you. I don't know if I'm the only one.
Oh, sorry, I forgot to unmute myself. Yeah, I was saying pretty fascinating talk. Like it's amazing how many different applications of machine learning you can find in manufacturing and how much of an impact it can have. Yeah, we'll probably have time for like one question. So let's pick the following one. Yeah, basically, if you guys fully succeeded, how big would the climate impact of that be?
Yeah, great question. Well, transportation is, call it 20% roughly of global emissions. And by moving from an internal combustion engine to battery electric cars, you can decouple then the fossil fuels from transportation. So you could go to electric vehicles on a dirty electricity grid that still uses coal, and that would get you about a factor of 2 improvement. But the opportunity that it offers is as you build up more renewables, or whether it be solar, wind, nuclear, or what have you, then you can go to a really fully clean transportation sector. And so, again, 20% of global emissions come from transportation. That's a massive part of the problem.
Mm-hmm. Yeah, that is indeed pretty amazing. And yeah, that explains why so much investment is going into this area. Yeah, thank you, Tim. I'm going to end the broadcast now and maybe see you at some of the networking sessions and see everybody else in the audience there.